This meeting is being recorded.
In 16.10, we're introduced to sigmatropic rearrangements, which are a specific type of pericyclic reaction where we have one sigma bond being replaced with another. So what we see here is this sigma bond highlighted in green on the left-hand side here is going to be broken, and those electrons will be moved up here. So that's what we see with this pi bond forming over here. At the same time, remember this is a concerted mechanism, so all three of these movements are occurring at the same time. This sigma bond is being formed over here, as we can see with this arrow right here, that formation of that new sigma bond. And then again, at the same time, these pi electrons are being shifted over here, so we have formation of this pi bond here. So we have, again, a rearrangement occurring, and one sigma bond is being replaced with another. So the pi bonds, we should note, as I mentioned with those arrows, they also will change location. So again, a concerted mechanism in this pericyclic reaction. And let's take a look at how these types of reactions are noted. So the notation for this is a different type of notation than we have seen before. So we have our sigma bond that's being broken, outlined over here, our sigma bond that's being formed with this specific product, again, shown over here on the right, highlighted in green, and then the atoms in between. So that's where the 3,3 sigmatropic rearrangement notation comes from. This 1,3 is from the top portion of this molecule, the three atoms in between the sigma bonds that are being broken. And then down here, we also have three more atoms that are between the two sigma bonds that are being broken and formed. So this is again a new notation, and it's the number of atoms, in this case 3 and 3, between those two sigma bonds. If we have this special case here, this is commonly called a 1,5 sigmatropic rearrangement. As pointed out over here, this we'll call carbon 1 or atom 1, and this bond that's highlighted between this carbon and hydrogen is being broken, and we see this bond over here between atom 5 and the hydrogen, so carbon 5 and the hydrogen being formed. And this is just the general structure, movement of atoms or movement of electrons, and then over here, our final structure. Sometimes this is called a 1,5 hydrogen shift as well. So you might see something like this because we're moving around that hydrogen atom. So 1,5 hydrogen shift is an alternate name. A specific type of rearrangement that we have only carbon atoms, so all 6 atoms are carbon atoms. This is called a cope rearrangement. And again, this is one of those 3,3 sigmatropic reactions, sigmatropic rearrangements. And then specifically, again, we call it a cope rearrangement. It's all 6 of the atoms moving around and the bonds being broken and formed between our carbon atoms. So the equilibrium, we should note down here, would favor our more highly substituted alkene, and that's what we see here, right? This alkene is di-substituted, or tri-substituted rather. Or no, I'm sorry, di-substituted, but it's more highly substituted than our starting material over here. So that's why the rearrangement occurs. Then we have this other specific case called the Klein rearrangements. These are, again, specifically the 3,3 sigmatropic reactions that occur when oxygen is involved. So now we have an oxygen analog of our cope rearrangement, and commonly we'll see an allylic group up top here. Or rather, this is our vinylic group. So we have our vinylic group here, and then we have down here our allylic. And you can see it extended here, allylic and vinylic. And then through heating, we can see that our equilibrium favors the carbon-oxygen double bond, which is more stable than the carbon-carbon double bonds. So again, stability favors this form here. And we see that that is our higher percent product. Last, we have another 3,3 sigmatropic arrangement. These are now allylic aryl ethers, and we can see through heating, we can form this rearranged product. And then through this equilibrium and this tautomerization, we can go between a ketone or an enol product through this tautomerization. And last, we see here a real-world example showing vitamin D, where two pericyclic reactions occur during the biosynthesis of vitamin D.